I wanted to give you guys a lot of examples in this video, but then it was going to be really long. So we're splitting up calculating rates of change into two videos to try to keep things manageable size. You can do a bit of practice after each one. Hello, Theodore. Sometimes I call him the door. Anyway, let's calculate rates of change. So, let's remember all the way back to 1.3 rates of change, average rates of change. We had a formula for that. The average rate of change was just the change in y, or the change in the outputs, divided by the change in x, the change in the inputs. We wrote that as delta y over delta x as shorthand. It just means the difference between the second y and the first y, the difference between the second x and the first x. Well, linear functions, we said in the last video, we said that linear functions have a constant rate of change. The rate of change never changes. So for linear functions, the average rate of change is the same as the rate of change period. Because if your rate of change is not changing, then, and it's weird to talk about changing rates of change, that's more fun in calculus. With second derivative fun. But anyway, so our slope of a line is the rate of change. And it's never changing. Lines have the same slope the whole time. And it's the same formula. We can write it with function notation on the right, or we can just use the same formula that we use for average rate of change. Let's do an example and use this. The population of a city increased from 23.4 thousand to 27.8 thousand between 2002 and 2006. So let's assume that the city's population grew linearly. Find the rate of change of the population during this time span. Well, this is really just like a 1.3 problem. Okay, but we need to come up with some, let's come up with some variables, some letters. Okay, let's say that P is the population. Let's be creative. Let's have P be the population in thousands of people. And let's say T is the years since 2002. And again, there's a bunch of different ways of setting this up. But depending on how you set it up, your answer is going to look a little different. Okay? So let's set it up this way and see what happens. So the slope then, well, we don't have y's and x's anymore. This function becomes P2 minus P1, the outputs, divided by T2 minus T1. Right? If we change the letters, then the formula changes accordingly. So this is our first population. This is our second population. Our first time is actually 0. 2002 is 0 years since 2002. And our second time is 4 years after 2002. So then our slope function becomes O. Also, P is the population in thousands. So technically, P1 is 23.4. P2, 27.8. So we get P2, which is 27.8, minus P1, which is 23.4, divided by P2 minus T1. So because I set up the problem in this way, I get to get rid of a ton of zeros. I get to write so much less. I'm so happy. So much less writing for me. But it might be more confusing. You could have the population just be the number. You could have T just be the year. You'll get the same answer, and that's why we have to interpret our answer at the end. When you subtract these numbers, we're going to get 4.4 on the top and 4 on the bottom, which equals 1.1. What are our units of rate of change? Units in output divided by units of input. So the output is thousands of people. 1,000 people divided by the units of input, which is a year. So what is the rate of change? Well, it's positive. The population is growing by, there we go, sombrero answer. What if I say Sombrero all your answers. You have to put all of your answers within sombreros. The possibility. All right, so that's how the population's changing. Positive means growing, slope is up, function's increasing. If it's decreasing, the slope will be negative. The rate of change will be negative. Doing another example. The pressure P in pounds per square inch, otherwise known as PSI, on a diver depends on their depth below the water surface. So if you're really far into the water surface, there's a ton of pressure on you. Which is why if people go really deep, then they have to they actually can't go all the way up. They have to pause at certain depth levels that their body doesn't, I don't remember the science, but it's called the bends or something is what you get. I don't know if anyone knows something about diving. You probably know what I'm talking about. Hopefully I'm not messing it up. Anyway, so the pressure depends on their depth, D, and according to this formula. So let's interpret the components of this formula, because what does this formula mean? It means that the pressure starts at 14.696 psi. And it has a variable component as well, that as the depth increases, the pressure increases as well. Let's look at this. This is our B, and this is our M. What do we know about lines? B is the initial value, the starting value, sometimes fixed cost. M is the constant rate of change. So let's start with B. So 14.696 is the starting value, which means when a diver is right about to dive, that's the pressure. That's the pressure of just our pressure at sea level, okay, above water at sea level, the pressure of our atmosphere. 14.696 is the pressure in, gosh, I don't know the right words to say, pressure in our atmosphere. Technically, you could say at sea level. I don't think it matters. No, it matters a little bit. I don't know. You're not graded based on your knowledge of physics. And then PSI. I didn't include units. That was important. You will be graded on your use of units. So that PSI is the pressure in our atmosphere. That's where we start. And then the pressure, right? M is our slope. We said if slope is positive, and right, this number is a positive number. Our slope is positive, it's increasing. So the pressure increases by 0.434 pounds per square inch every foot the diver goes deeper in. English is hard. Every foot deeper the diver dives. I don't know. It doesn't have to be pretty. Just communicate the idea. And that's what we've got here. And this example is one of the most important examples of this whole section. Okay? Can you interpret what a function means? And just like we did in the first example of this whole section, can you put words into a function? Function into words, words into function. That's the most important thing in this section. Something like this. Okay? And it's going to be this kind of idea going forwards. We'll get some more practice of this in the future videos and in the homework assignment. And let me know if you have your own questions, and bye-bye.